Okay, so let's continue on with our last example where we have an object moving horizontally, being dragged across the floor. Say you have a rope, and if you're just like standing up while you're holding the rope and you're walking, you're holding it at some angle, we'll call it 40 degrees from the horizontal, and you're pulling with a force of 30 newtons, and there's friction on the floor that has a coefficient of kinetic friction of 0.5 newtons, and our mass is 10 kilograms. Okay, so in this, thinking about the questions that we could ask, when you go back to the forces unit, right, we can think about drawing a free body diagram. And what that allows us to do is to ID all forces acting on the object. So go back to our third check-in, and we were asking about the forces that were acting on our boxes, and we can draw free body diagrams for them, and that could be something that can be asked here. The other thing is, what's the acceleration of this box? And one of the things, now that we have two dimensions, we have x directional motion and we have y directional motion because we have a pull, right, from or we have components of this pull because it's at an angle. We can talk about the acceleration in the x direction and /or the acceleration in the y direction. But the way that this problem is written, right, it says that we're moving horizontally. And what that means is that our AY has to equal 0 because moving only horizontally. Right, so if we have multiple forces, we have to understand what's happening with the motion, and our net force, because we're only moving horizontally, has to be in the x direction, right? We understand that force is a vector and acceleration is a vector, and whichever direction our net force is acting, the acceleration is in that direction. So if there is no net acceleration in the y direction, then the only acceleration we have is in the x direction. So let's go about drawing the free body diagram for our object here. Okay, and remember, the free body diagram shows all the forces acting on that object. So remember, all objects have an mg force. This object is on a surface, so it's going to have a normal force up. And remember, the normal force is situational. Like, you cannot right now, only having drawn these two forces, say that the normal force is equal to the weight force because we haven't drawn all of the forces. We have some pull force going up and to the right at a 40-degree angle. And then because we were given a coefficient of friction, that means that there is friction in the opposite direction of the motion. And if we're moving horizontally to the right, the friction has to be horizontally to the left. Okay, so this would be the free body diagram because that pull is happening at the 40 degrees. But another way that I like to represent this free body diagram, because we really just work in the x and the y, is to draw all of these vectors again, but to really emphasize that this pull force, right, if we go back to the original diagram, I'll do it in, I don't know, I'll do it in this, it's related to the purple, this purple, right, we have this pull force has some x component, we can call that pull x, and some y component. So that is really what is going into the motion of this object. We have the pull y and we have the pull x. So doing the free body diagram the second way, really tells us how many forces we have acting in the y direction. Now the pole has a value of 30 newtons, but the pole y and the pole x will not be 30. It can't be 30. But there is some component of the pole that is going in the y direction and some component of the pole that is going in the x direction. And the reason why we want to do this, right, we want to identify all of these forces, but in the end, we want to know what the acceleration is, right? And our acceleration is dependent on the net force. So if we think about our F net in the x direction, okay, think about what's going on here. There's two forces acting in the x direction. The force of friction and the pole, or the component of the pole in the x direction. Okay, so our F net, or technically we're just thinking right now about the x, right? The net force in the x direction is going to be equal to the pole component of the x, or the x component of the pole, minus the force of friction kinetic, because they're going in opposite directions. Now, our net force is always equal to ma. We can do the same thing for the y, but in this case, looking at the y, we see that there's three forces, right? We have the normal force and the pull force, the y component of the pole going in the up direction and mg going down. So this absolutely matters when we are doing the net in the y direction. We have F normal plus pole y minus mg is equal to mass times acceleration. Okay, so all I did was looking at our free body diagram and writing Newton's second law for our x direction and our y direction. Okay, going back to kind of one of the previous videos, right, we can add vectors easily if they are in the same axis. That's what we're doing. We're just pulling x's and y's and putting those together. Now I'm going to stay on the y side because we talked about up here that AY has to be 0 because it's moving horizontally, right? So it doesn't matter what the mass of this thing is. I know it's 10 kilograms, but F net in the y direction has to be equal to 0. So our net force, or our normal force, plus our pull of the y direction is going to be equal to mg. Okay. If we come over here, it is possible that you could have a 0 acceleration in the x direction, but it is not guaranteed that that's what we have. So we cannot assume that the right side of this F net x is 0. So we have to go through this calculation with all of our numbers, right? So we have pull x minus F the friction, that is kinetic, is equal to ma. And all I'm going to do now is solve for the forces, because we have two things that we're doing. We're trying to solve for all of the forces that are acting on this object, and we're trying to solve for the acceleration. So the acceleration here, right, we're technically talking about acceleration in the x. We want to solve for this a, but before we can solve for this a, we have to put in all of this other information. So there's a little bit of work to do. So what we can do is take our pull force, which is 30 newtons at 40 degrees, and we break that into its components. We have pull x, which is adjacent, so we are going to do 30 cos 40 to get our pull in the x direction, which I get 22.98 newtons. And then we have pull in the y, which is opposite, so that's going to be 30 sine 40. And that comes out to 19.28 newtons. Remember, we assess the fact that we are going to the right in the x, so that's positive, and we are going up in the y, so that is also positive. Okay. So this helps us, right? The pull x and the pull y our values that we have in these equations. So we have now identified these portions of our of the force. Okay, so we know the mg value. I'm just going to get rid of these. Okay, so in our free body diagram we can write the values that we know. So mg is the weight times acceleration. The weight is 10 newtons, acceleration is 10, so we have 100 newtons of force going down. And we cannot say that the normal force is equal to mg because we have a calculation right here that says that the normal force plus the pole y is equal to mg. So you cannot have a normal force of 100 newtons if the mass is 100, because if that was true, then pole y would be a net force in the y direction, which would cause acceleration going up. So what we can do is we can solve for the normal force. I'm going to take this equation, and I'm just going to rearrange it. The normal force is equal to mg minus pole in the y. Right, I'm just looking at the equation that's boxed in green and solving for the normal force. And we can plug in, now that we've broken our vector into components, mg is 100 newtons. Our pole in the y direction is 19.28 newtons. So we get a normal force of 80.72 newtons. Okay, and that's going in the up direction. We can put that here. 80.72 newtons. And if you want, we can put the pole y in. I don't even know what color I want. Pole y was equal to 19.28 newtons. Now, right, it should make sense that the when you add the normal force and the pole force in the y direction, it has to equal 100 because there is no acceleration in the y. So we just got that one. And now we need to solve for the force of friction. So remember that our force of friction equation is equal to the mu times the normal force. Okay, so it is so important that we solve for the normal force in order to solve for the frictional force. So friction is equal to, our mu was 0.15. Our normal force, 80.72. So you can, like, I'm going to say it again, the normal force is situational. So you can't just assume that the normal force is equal to mg. You have to look at your net force in the y direction and get an equation for what the normal force is. If there's only two forces that are in the y direction, the mg and normal, then yes, those two are equal to each other. But if you have more forces that are going on, like you're pushing down on something, you're pulling up on something, you have to pay attention to that equation. Okay, so our force of friction that we get here, I get 12.11 newtons. So we can put that in here. And then we know the pull in the x direction was calculated at 22.89. So there is, or 98, sorry, there is a net force in the positive x direction. So this thing will be accelerating to the right. And what we're going to do to find the acceleration is we're just going to take this equation, right, our F net equals ma, and we know our pull x, 22.98 newtons. We know our force of friction, 12.11 newtons. And that's going to be equal to the mass, which is 10 kilograms, times the acceleration. And I'm just going to be clear and say that this is the acceleration in the x direction, so a sub x. So if we solve for this equation, we will get 1.09 meters per second squared. And since we're talking about x direction, we know that this can be either positive or negative, and it's moving to the right. We should absolutely call to the right positive and to the up positive. So our answer, by giving the direction of positive, is giving us the directionality of that